Right. Okay. Thank you. Thank for the inviting me for this meaningful workshop. Uh, my name is Kwangkeun Yi from Seoul National University, Korea. And let me start with these three photos. Rightmost photo is our group, and actually left two photos that I took when Patrick and Radia visited us. First photo was about quarter century ago, almost. And when we invited him, I was not lucky enough to be ENS student to learn abstract interpretation from Patrick, but actually we were brave to invite him over to Korea to give a 1 week, 9 to 5, 5 days in a row, full tutorial about everything about abstract interpretation. That was, and the first photo was one that I took him when he was in my office at that time. And it was unforgettable 1 week memory. Okay. And the second photo was we invited Radia and Patrick again about 10 or 15 years ago as a departmental distinguished lecture, and also to celebrate the opening of our research center. Yeah, at that time we were fortunate to have a very generous grant from Korea Research Foundation. Okay, so in this talk, I'd like to share with you what we have done for program analysis and also for program synthesis based on abstract interpretation. And the title of this talk is about program synthesis that I worked with Yongho and Woosuk. And actually, the synthesis part will comprise 2/3 of my presentation. And the remaining 1/3 will be about the brief review about what we have done for analysis part, okay? All right, so our story of abstract interpretation. So two parts, analysis and synthesis. So for once upon a time, after we learned from Patrick about abstract interpretations and so on, we became curious whether we can build realistic analyzers to find some real bugs in real C programs. So we ventured out to build a static analyzer based on abstract interpretation framework for almost a full set of C programs. And I said it's more sound, so it's more sound than less sound one. So it has we try to have as little assumptions possible about the semantics of C. And after we built this workshop, we tried to experiment it with against some open source C programs and Linux, some device drivers of Linux and so on. And we found that the tool can really find some meaningful bugs. So we are excited. So after that, we branched it to why not commercialize it. So it has been more than 10 years, and now the company become a bit stable. So now they boast about static checkers for safety and security errors for more than 25 programming language. And on the way of commercializing it, as you all know, we had to give up lots of good things about the soundness and so on. So lots of compromises happens there. So we had a very hard time to commercialize the workbench version into a commercial product. And one branch was that. After that, we decided to come back to the academic university lab, and we scratched our head that okay, without those compromises from the beginning of the workbench, that is a global sound analyzer for C programs, we are curious of how much we can do about the scalability and the precision of the analyzer. So we managed to come up with a interesting framework that we call it sparse analysis framework that can improve the scalability without any compromise of the soundness of the analyzer. And after that, the second part is about what we can do about precision. Okay, so we'd like to have a cost-effective way of improving the precision without again compromising the soundness and so on and so forth. So we managed to come up with some interesting solutions that we like, and everything was available in the open GitHub. And that was our story about the static analysis based on abstract interpretation from an angle of abstract interpretation in practice. Okay. And after that, more recently, we also doing interesting work on program synthesis based on abstract interpretation. So thanks to abstract interpretation technique, we achieved a superb performance in program synthesis. They can beat other competitors. So actually the underlying abstract interpretation technique is fairly simple and standard thing, like a bidirectional analysis, forward backward analysis, and we are using a combination of domains and something called the reduced product, and sometimes we do a finite refinement, kind of abstraction refinement, and so on and so forth. So using those three very standard, simple-minded technique that has been done in abstract interpretation, we can achieve nice performance in program synthesis. Okay, so I will present the synthesis later, and before that, I will give you a brief overview of our analysis things about the sparse analysis and selective extensivity things. So this slide is about commercialization. Okay, so actually the colorful figures are the snapshots of the company's web homepage, and they are boasting about advanced static analysis and so on and so forth. And actually, those are based on our lab workbench that has been developed on the abstract interpretation framework. Okay, so the point of this slide is the last line. Thanks to abstract interpretation framework, we were able to build a realistic global analyzers for the almost full set of C programs, and based on that, they are doing a kind of commercializations. Okay, that was very nice. And after that, as I told you, we came back to a lab, university lab, and we try to understand. We try to see how far we can do for scalability. So, given a sound and global version, and we managed to come up with a we call general sparse analysis framework. And by using that one, just look at the graph there, the performance improvement is very impressive. It's almost like an exponential improvement in scalability we achieved. Okay, and we dare to say general because it's based on the abstract interpretation framework. Okay, yeah. So at the time when we were able to analyze globally analyze a C program from the main procedures. 1 million lines in 10 hours in the usual laptop machine. Okay, that was the performance at that time. The idea is that we tried is to exploit the semantic sparsity. By that I mean there's two sparsities in the semantics. One is a spatial, we name the spatial one, and the other one is a temporal sparsity. And spatial. Okay, I will briefly give you the intuition about the spatial and temporal sparsities later. And before that, our framework is like this one. Given an abstract semantic function f sharp, we give the guidance how to make it sparse. Okay, so sparse, and still we can guarantee that the original the analysis accuracy is preserved after the specification. That was very nice. And actually, the point of this slide is this one. After we report this result to the community, and one comment that I like is this one. The theoretical result is very general, thanks to abstract interpretation, because everything is in top of the abstract semantics. And it could be applied to many other analyses. PLDI papers have been accepted that were simply instances of this framework. So this was quite a thankful comment. And again, we achieved this one because thanks to the abstract interpretation framework. Okay. And the idea of this spatial and temporal localization is fairly simple. Let's focus on this graph. Suppose the straight line code of C-like programs. And actually, the blue boxes, okay, we are doing a flow-sensitive analysis. For each program point, we try to estimate the machine state of C programs. And in each machine state, let's focus on the blue box. We try to record the memory map that can happen at the point during the executions. So this program has 6 memory locations. So for every program point, we record the whole machine state. And that is actually the waste. Because let's focus on the orange box, because at each statement, the statement will use only a small part of the memory state. So we don't have to record everything. Instead of that, we can just record the orange box that is small, just a fairly small portion of the whole memory state. Okay, so that is what you mean by spatial localization. So it's reminiscent of in the separation logic, frame rule, that kind of thing, or in static analysis, the abstract garbage collection thing. Okay, so each program point, we just record the small portion of the machine state. That is enough. And about the temporal localizations is that we don't have to, during the program analysis, during the abstract interpretation, we don't have to follow the sequence that is explicit in the program text. Actually, it's enough to follow the semantic dependencies. So instead of following the black arrows that is explicit in the program text, we can just follow the express line, the orange arrow. That means that after we define the x value over there, then the result state, we don't have to pass it along the flow in the program text. We can just pass that newly defined x image to the next use point. Okay, so that's what I mean by temporal localization. So we can use these two kind of sparsity in the semantics, try to fully exploit it to make our analyzer economical as possible. Okay. So we achieved that impressive performance improvement by this framework. And then after that, we scratched our head again to how to improve the precision in a cost-effective way. Okay, so actually we kind of, this is a kind of exaggerations, but anyway, we try to improve the precision thing. And our idea is that we can apply the precision improvement technique only selectively. So precision improvement here is not applying a different, elaborate domains. No, given an abstract, we just focus on the flow sensitivity and context sensitivity. So instead of blindly turning on the sensitivity for every function call, we try to selectively apply the context sensitivity for a particular function calls only. If that sensitivity improves the accuracy of the final result. Okay. So the idea is, the diagram says that, okay, so the blue, the star is the actual set of program state, and the green one is an over approximation that we compute during the program analysis. And suppose the red blob is the error state. And instead of improving the accuracy for every corner, that is costly, it's enough to improve the accuracy just around the error state area. Okay, that's the key idea. And our method achieved this interesting performance number. We pay 28% more to reduce the 20% false alarms. Okay, if you do the blind, naive context-sensitive analysis, for example, 3 K CFA, 3 CFA, and the performance cost increased about 1,300% more, just to reduce that similar size of the memory false alarms. Okay, so we designed. So the question is that, how do you know how do you know which function call we have to turn on the context sensitivity? That is the question. And then before the analysis, we'd like to determine it. Okay, so it's kind of catch-22 situations. To analyze very effectively, we have to analyze the future of the impact of the context sensitivity. Well, the solution is a very simple one. We just design a pre-analysis. Okay, so that pre-analysis is that we put the context sensitivity as high as possible, say 100, whatever. But we are using only 2-element domain, and that 2-element domain basically says that, okay, no effect. Okay, just analyze, just apply the pre-analysis. Then each function call, it shows that, okay, this is good one. This one you don't have to put on context sensitivity and so on. Okay, And again, yeah, thanks to the AI framework, it's easy to define that kind of pre-analysis, right? And we applied that one. And later, we also try to apply the machine learning technique, Bayesian optimizations, for linear score function that scores the context-sensitive effectiveness for each function call. And depending on the score, we turn it on and off, okay? So actually, in order to do that, we, design, so side cost is that, okay, we have to design the new analysis, the pre-analysis, or we have to train the analyzer for Bayesian optimization to figure out the linear score function. And actually, having a pre-analysis design to us, I mean, it was easier and quick. Okay. So this is the thing that we have done for developing a static analyzer, realistic static analyzer for C programs, and having some interesting, drive to improve the scalability and precision improvement. And we come up with the interesting techniques. Okay. So this is it. And now, from now on, I'd like to show you our most recent works that we have done on program synthesis. Okay. So the target of the technique, synthesis technique is the inductive synthesis one. The input is a grandma, and the input-output pairs. And the output of the goal, we need to have an automatic program that automatically generate a right program that right program in that grammar that satisfies the input-output pairs. Okay. So for example, this grammar is a bit manipulation expression grammar. X is an input. 0001 is a 4-bit binary string constant, and shift and or exclusive or blah blah blah. Okay. And then second input specification is an input and output. 1011. And it must return 0011. What would be the function? There can be many, right? But we come up with the goal is that to try to have a fully automatic system that build this output. So believe it or not, this function will generate the 0011 given 1011. Okay. All right. So this is a setting. So actually, the automatic synthesis examples, the tool that we developed, I'd like to impress you with some examples. So bit manipulation operator syntax, given a 5 to 20 input-output pairs, it can generate within 1 second or up to 35 minutes, can generate these functions. See, given a 8-bit string, it can generate the absolute number. Believe it or not, that bit manipulation function does that one. And it can generate that procedure, that expressions by program synthesis. And sign function is given a 8-bit string, whether it's positive, negative, or 0, it can generate, by using that operations, it can return 0, -1, or 1. So without using any if branches, there's no case analysis. So this is very tricky, interesting thing. And average flow, average ceiling with the unsigned 8-bit, this function is automatically generated by given a 5 or 6 or 7 input-output pairs. It's very interesting. And another thing is that one interesting application of program synthesis is de-obfuscation. Given a very complicated, obfuscated program, we can generate the input-output pairs, and then we feed the input-output pairs to our system, and it can generate a more readable program. Okay, so it's kind of de-obfuscation. So actually, the last example was the one that took 35 minutes, given 20 input-output pairs.
The way you do the last one is that by taking the obfuscated program and run it like 20 times, you
collect the input output, and then feed it to okay. Yeah. Yeah. All right. So this is the thing, and actually our system, we name it Simba. The x-axis are the number of other competitors, including ours, and the y-axis is the number of solutions that can be generated within the same time bound, and our performance is very, very good, thanks to abstract interpretation techniques. And as you see in the followings, the things that we use is a very simple thing, very simple 3 techniques in abstract interpretation. Okay. So synthesis key is how to prune the huge search space. Okay. So given this bit manipulation syntax, and given this input-output pair, what we do is a kind of hybrid of top-down and bottom-up. From top-down, from the beginning of the S symbol, okay, non-terminal symbol, following the grammar, we expand it, and at some point we stop, and then we're using some constant things. We compose some small expressions and try to plug into the non-terminal symbols and see if whether that satisfies the given input-output pairs. Okay. All right. Now, as you see, the X is definitely not the solution because 1011 returns different one. Okay, so it's not an identity function. Suppose the second X marked subtree, X shifted by some expression, and then we know that before expanding further, before we search more, we know that X shifted by something cannot satisfy the input-output pair by any way. Whatever expression we plug into that box, there is no way that satisfies that input-output pairs. So the interesting cute analysis problem is that given a partial program with one more holes in a program, we try to understand the possible value and see if whether it can satisfy the input-output pairs or not. All right. So naturally, we do both. As you see, we are very fortunate in a sense that this grammar does not have any loops, no function calls, no if branches, and very simple bit operations only. Only challenge is that there's one or more holes in the program. Well, analyzing that possible value of that one is easy because we can just assume that the box can be any value. So assuming that the input is a 4-bit, so forward analysis, we can, given a particular input 1011, we can conclude that the value of the output would be, this one would be top, and join the O operation, we can generate the one top one. It's very simple. And we know that, that cannot be 0011. So definitely we have to stop expanding those partial program anymore. So discard it. But forward analysis is not complete enough. So for example, that a slightly different partial program, X, exclusive OR, and box. Okay, and we'd like to see whether we have to continue exploring the subtrees or not. And by the forward analysis, the conclusion is that, okay, X given 1011, X exclusive or something that we don't know, they can generate the top. So no information. So there is no trimming is possible. So because we know the output, we can do a backward analysis too. So it's also easy because the syntax is fairly straightforward, single line of expressions. And given this output, given this partial program, we do a backward analysis and we come up, because X is known, and we can conclude that the box must be 10000. Okay, and then when we expand this box with different expressions, we can some subtrees we can trim it because this part, this expression is for the box, and box value must be 1000, but there's no way to make this expression become 1000. Believe it or not, and divided by this box cannot be this one either. So we can safely trim the, stop exploring the left two subtrees. Okay. And so the forward and backward analysis was fun to do, and we can trim some subtrees during the search phase. But it was not enough. And also in competition with other tools that does not use the analysis, but using a collection of heuristics, but very quick to explore very huge space. So in competition with those tools, the time constraint is very short. Because if we spend more time in analysis, then we lose. Okay, so our analysis must be very quick, and would like to be very, as precise as possible. And we found that, okay, for the backward analysis, okay, is not enough. And we have some time budget still remains. So we try more. And that is that we use the different domains and try to refine the results of each other's. Okay, I mean, in this audience, I think you know all this. And we found that just the bitwise domain and unsigned interval and signed interval, 3 domains are enough to improve the accuracy of bit within that time budget. And the bitwise domain top 1 0, and suppose we come up with in the interval domain 0 6, then we can refine each other. Okay, we refine each other, and we come to the 0 top 1 0 and 1 5. Okay, so we improve it a bit together, and we are using that one too. And still, we improved a bit more, and we figured out that, there's still some time budget remains, and we'd like to do more. And at this time, we'd like to some kind of on-the-fly refinement, finite refinement. And in this case, bit thing is only 1, 0, and 1, so always finite. So we can do abstraction refinement. So for that partial program, we do forward analysis. There's nothing we can gain. By backward analysis, we can collect some more information about the box. Box must be top 1. Okay, and on the way of doing that, we think that we can do refinement at this point. So instead of trying 0 top 1 1, we can finite concretizations kind of thing. It can be 0 0 1 1 or 0 1 1 1. Okay, so we try to figure out what would be the value of a box for that expression to be 0 0 1 1 and separately 0 1 1 1. And we come up with the 2 solutions of box. And then finally, single solution for box would be the join of those 2 solutions. And by doing this, we can improve the information of this bit from top to 0. So very small improvement. And it also helps us to improve the accuracy within the constraint of the time budget. So using this very standard and cute applications of the 3 techniques in abstract interpretations, we were able to beat the existing program synthesizers. And we built the whole system. And this graph shows that the top graph is the same as the before in a colorful manner. And actually, that is the graph that shows the number of the fastest solved problems of each domain. So it shows that our tool Simba was very quick to zero in on the solution. Okay, and the bottom graph shows that given a 1 hour budget, actually other tools can catch up, but still absolute number of solutions are less than ours, except the comparable cases of where we try to build a bit manipulation program with the condition expressions. Then it's okay. So this is my story, open abstract interpretation and analysis and synthesis. In analysis, we try to do some kind of limit that we think interesting. One is commercialization, and the other one is on the sound and global analysis workbench. We try to improve the scalability. What techniques we need to improve the scalability and cost-effective precision. And synthesis part, we're also using fairly standard, simple techniques in abstract interpretations to achieve a very good performance in program synthesis for bit manipulation programs. Okay, so in retrospect, I think this is definitely true, at least for me. Without AI frameworks, without understanding, knowing, having this framework and concept or vocabularies, we might have failed to conceive and develop our methods. Okay, I've been too scared of the sheer complexities of the reality. The C programs, I don't think if we didn't understand, you didn't know the abstract interpretation framework in the beginning, we couldn't imagine to build a static analyzer for the full set of C. That was definitely true. And so, so without having that knowledge, having that mindset, maybe even though we try to build something, maybe we have no understanding of what we are doing, and therefore we fail to communicate our method to the community. So, okay, so this is it. Thank you very much. All right. Do you have questions? Yes.
Thanks for the great talk. I'm wondering, in your top-down synthesizer,
yeah,
it's possible that you could generate some programs like box, XOR box, or something where there's really very little that an abstract interpretation can do.
Yeah.
So how do you decide when to run your interpretation, or do you somehow avoid generating terms that are too?
Yeah, the term must contains only, usually contains the input variable. It helps a lot. Yeah. We can still do something. No. Okay. Yeah.
And you mentioned that there was also a bottom-up.
Yeah. Yes.
When
yeah.
do you switch it? When do you decide? How do you decide when to switch it?
Oh, actually, what you do is that we do an expansion up to two phases, and then we try to fill it up. Yeah. And yes.
In one case of these synthesis examples you showed, how many times would you invoke the abstract interpretation during such a run?
I don't have that number.
Oh, but what of magnitude?
It was very quick, less than a second. So
you must run the abstract.
Oh yeah, the analyzer. Oh yes. Oh yes. Oh, I don't know. Really, we didn't measure. Yeah.
But it seems like there's a basic idea of abstract interpretation of partial programs.
Yes.
A lot of times people do abstract interpretation of complete programs.
Right.
But this is
yeah. That's what I say. It's a cute problem. Yes.
Two questions. Are you guaranteed to find the smallest program or
no
shallowest program?
No, there is no such guarantee.
And did you try it for other domains except just bit manipulating?
Yeah, this is the first one, and we try to work on string manipulation program. But for string domain, the backward analysis is fairly complicated. So we sort of discouraged.
Thank you.
Yes.
So the microphone just behind you.
Oh, okay. Hi, thank you for the talk. Just a simple question on the scalability part. You said that for sparsity, you kind of analyze where, for example, in the first node, the memory state you will use, and then you can skim support.
Right.
I just didn't get what you do. Is it a syntactical analysis there?
Oh, okay. So actually, this is again the kind of catch-22 situation. Before we do this kind of sparse analysis, we have to know beforehand for each portion of the program what memory locations will be accessed. Okay, so what do you do? Pre-analysis.
Yeah, and so my question is it a syntactical one, semantical one? Because I don't know if a semantical one in big project could just slow a lot the analysis.
Yeah, this one, the example is fairly straightforward. It's explicit from the program text, but for arbitrary C expressions that follow, lots of pointers and so on and so forth, we have no idea from the program text which memory location will be accessed.
Okay,
yeah,
thanks.
We have to do some kind of analysis.
Okay, thank you.
Yeah.
Any other question? I may have one.
So you have a static analyzer, and then you did program synthesis.
Yeah.
Can you synthesize a static analyzer?
No, I don't know. I don't know. Why not in 10, maybe 20 or 30 years? Yeah. We tried ChatGPT.
Oh.
No future yet. Fortunately. Yes. Yeah, actually, we tried. We tried some simple examples, and they gave a random program. They gave a completely random program. Yeah. So. You can try it. I mean, here. I mean, given this grammar and.
Can you use it as a first guess that you can refine then?
First guess? What do you mean?
I mean, it has some intuition, but it's wrong. But then it gives you, it leaves you on the good path.
The input-output pairs. Oh,
so
I see.
You use it as a, I guess, and then you.
Yeah,
you
I tried 5 or 6 times interaction with the ChatGPT to guide him, but still it generates a random code. So I forget. Yeah.
Can you pass?
Yeah, just I'm very naive with program synthesis, so I just wonder what it will involve to just expand the grammar with other construction and like loops and conditional branching.
So your question is, how do we expand?
Yeah, well, what will it involve? I'm very naive to the domain, so.
I mean, given this one, we do not use any heuristics. We just blindly expand breadth first.
No. It was about expanding the grammar, like handling other kind of program. Yeah.
Oh, I see. Yeah, we are very careful, because if the program has an if or loop, then how do you do the backward analysis? Do you know how to do it precisely?
Depends on the kind of analysis, I guess.
Oh, okay, maybe.
Yeah, I don't know.
Maybe, yeah. It's a challenging thing, right?
Any last question? So maybe I have one last one. Sorry.
Oh, okay.
Yeah, sorry. So when I look at the formula that has been, synthesized, it seems very similar to an old book that we read a lot, which is called Hacker's Delight.
Yeah, exactly. Yes.
Have you compared?
Exactly. Oh, yeah,
this kind of stuff.
Exactly. Actually, the benchmarks. One of the set of benchmark is the Hacker's Delight.
Oh, okay.
Yeah, that's the. Yeah, I think these are from Hacker's Delight. I think.
A follow-up question, because so some of those formulas are very much Hacker's Delight-like. However, x shifted by x is really strange, because it's defined only for pretty small values of x, like between 0 for 8-bit numbers, maybe between 0 and 7 or something like that. So that's something you will never see in Hacker's Delight. So what semantics do you give?
I thought these are in Hacker's Delight, no?
No. What semantics do you give to 128 shifted 128 times?
I mean, it's a very naive definition. The shift arrow is just
zero.
the usual, shifting, and 3 arrow is the shifting that preserves the sign bit.
Yes, but what if you shift by more bits than you have in the number?
Just to keep shifting, and it generates the 0000.
That's not defined in C and in most actual programming languages. So there's something a little bit fishy with those x shifted by x formulas. It depends a lot on the semantics you actually give to the shift. That's my only observation. But yeah, the average formulas are just wonderful.
I thought that this is the exact solution that appears in Hacker's Delight.
I'll check.
I didn't check either.
Thank you very much.
Okay.